And welcome back. As we go ahead and finish up our cosmic journey through our own solar system, let's go ahead and discuss the atmospheres of the giant planets. So when we start talking about atmospheric composition, we of course have reviewed this a little bit by introducing the idea that hydrogen and helium play a very important part. Now, at first, astronomers thought that methane and ammonia might be the main constituents of planets like Jupiter and Saturn, but now we know that hydrogen and helium, of course, are the dominant gases. Now, this confusion arose because neither hydrogen nor helium possesses easily detected spectral features in the visible spectrum. And it wasn't until the Voyager spacecraft measured the far infrared spectra that a reliable abundance for the elusive helium could be found. Now, the compositions of Jupiter and Saturn are generally similar, except for on Saturn, there is less helium. The most precise measurements of composition were made on Jupiter by the Galileo Entry Probe in 1995. As a result, we know the abundances of some elements in the Jovian atmosphere even better than that we know within our own sun. So let's first start talking about clouds. The clouds of Jupiter are among the most spectacular sights in the solar system. They range in color from white to orange to red and brown, swirling and twisting and constantly changing kaleidoscope of patterns. Now, given the cool temperatures and the composition of nearly 90% hydrogen, the atmosphere of Jupiter should be nearly colorless. So one hypothesis suggests that perhaps colorful hydrogen compounds rise from within these warm areas. Now, if we look at Saturn, you'll see it shows similar but a more subdued cloud activity, whereas clouds have a nearly uniform butterscotch hue. Now, if we look at the atmospheric layers, of course we already know our composition, but if we look at the atmospheric layers of these four planets, we'll see that different gases freeze at different temperatures. At the temperatures and pressures of the upper atmospheres of Jupiter and Saturn, methane remains a gas, but ammonia can condense and freeze. The primary clouds that we see around these planets, whether it's from a spacecraft or through a telescope, are composed of frozen ammonia crystals. The ammonia clouds mark the upper edge of the planet's tropospheres. Above that, of course, is the stratosphere, which is the coldest part of the atmosphere. And you can see here we have Jupiter, Saturn, Uranus, and Neptune, and of course, how the temperature can behave as we pass through those respective atmospheres. So let's go first by diving deeper into Jupiter's atmosphere. Above the visible ammonia clouds in Jupiter's atmosphere, we find the clear stratosphere, which reaches a minimum temperature near 120 Kelvin. At still higher altitudes, temperature rises again, just as they do in the upper atmosphere of Earth, because here the molecules absorb ultraviolet light from the sun. The color clouds are due to impurities, which is the product of chemical reactions among the atmospheric gases in a process we call photochemistry. In Jupiter's upper atmosphere, photochemical reactions create a variety of fairly complex compounds of hydrogen and carbon that form a thin layer of smog far above the visible clouds. If we were to dive deeper into Saturn's atmosphere, we're going to find that the visible atmosphere of Saturn is composed of approximately 75% hydrogen and about 25% helium, with trace amounts of methane, ethane, propane, and other hydrocarbons. Overall, the structure for Saturn is going to be very similar to that of Jupiter. Now, the temperatures are somewhat colder, however, and the atmosphere is more extended due to Saturn's lower surface gravity. Thus, the layers are actually stretched out over a longer distance when we start looking at Saturn. Overall, though, the same atmospheric regions, condensation cloud, and photochemical reactions, apart from the hexagonal wave pattern around the North Pole, are what we're going to find on Jupiter. And of course, that hexagonal wave pattern, if you haven't ever seen it, it literally looks like a giant hexagon sitting at the North Pole. Well, what about Uranus? Well, if we dive deeper into Uranus' atmosphere, unlike Jupiter and Saturn, Uranus is almost entirely featureless, as seen at wavelengths that range from the ultraviolet to the infrared. Calculations indicate that the basic atmospheric structure of Uranus should resemble that of Jupiter and Saturn, although its upper clouds are composed of methane rather than ammonia. However, the absence of an internal heat source suppresses up and down movement and leads to a very stable atmosphere with little visible structure. Now, what about Neptune? Well, Neptune's atmosphere, its upper clouds are composed of methane, which forms a thin cloud layer near the top of the troposphere. Most of the atmosphere above this level is clear and is transparent, with less haze than what we find on Uranus. Now, the scattering of sunlight by gas molecules lends Neptune a pale blue color like that of Earth's atmosphere. Another cloud layer, perhaps composed of hydrogen sulfide ice particles, exists below the methane clouds. Unlike Uranus, Neptune's atmosphere has convection currents emanate from the interior, powered by the planet's internal heat source. These high-altitude clouds actually form bright white patterns against the blue planet underneath, as we can see here in this image. So, let's talk a little bit about the winds and weather on our giant planets. The atmospheric motions we see on these planets fundamentally is different from those of the terrestrial planets that we visited previously. The giants, first off, spin faster, and their rapid rotation tends to smear out of the circulation into a horizontal or east to west patterns parallel to the equator. In addition, there is no solid surface below the atmosphere against which the circulation patterns can rub and lose energy. Deep convection currents of rising hot air and falling cooler air circulate throughout the atmospheres of planets in the vertical direction. So, that's enough to talk about clouds and stuff like that, but let's look at specifically a few storms that happen on the giants that are of great interest. The first, of course, is the Great Red Spot, which you probably have heard of. The largest and most famous of Jupiter's storms is the Great Red Spot, which is a reddish oval in the southern hemisphere that changes slowly. This giant storm has persisted in Jupiter's atmosphere ever since astronomers were first able to observe it more than 300 years ago. However, it has continued to shrink and become more nearly circular, raising speculation that we may actually see its end within a few decades. Now, there are three smaller but similar white ovals that formed in the 1930s, and you can see one of them here in the image right below the Great Red Spot. Now, there's also another big storm that we could talk about, which is the Great Dark Spot. Now, despite Neptune's smaller size and different cloud composition, the Voyager probe showed that it had an atmospheric feature surprisingly like Jupiter's Great Red Spot. Neptune's Great Dark Spot was nearly 10,000 kilometers long. On both planets, the giant storms formed at the latitude of 20 degrees south, had the same shape, and took about the same fraction of the planet's diameter. Now, the Great Dark Spot rotated with a period of about 17 days versus about 6 days that the Great Red Spot had. However, unlike the Great Red Spot, the storms on Neptune appeared to be short-lived, as the Great Dark Spot had disappeared when it was observed by the Hubble telescope. Now, of course, there are other spots that have appeared on Neptune that kind of periodically come and go, but of course that has led us to conclude that unlike Jupiter, which is able to sustain these storms for long periods of time, on Neptune they seem to be much more brief.